I explained to you already sometime if the W dot and WC dot, they move in the same speed, in the same directions, then the T dot will be equal 0, will be less than 0. Now, I also asked, if this is the case, for a asymptotically stable system, if n larger than 0 and 0 larger than 0 and k larger or equal than 0, then we know T dot always less than 0. So we have called asymptotically stable. Now, for any mechanical system like this, you don't have to solve eigenvalue. There's two ways to see the system is stable or not, or asymptotically stable or not. That's two ways. One way to do it is solve the eigenvalue of the system. All right? Now, one way to see the stability, to see the system stability. All right, the system stability. We can look at the eigenvalue of the system. Now, if the real parts of the eigenvalue are negative, then the system is the asymptotically stable. Okay? So that's one way to do it. The system stability with the eigenvalue, all eigenvalues of the system, the real parts of the eigenvalues, means all eigenvalues are negative. Then the system is asymptotically stable. All right. If any eigenvalue has 0 real part, any eigenvalue has the 0 real parts, and all other eigenvalues have negative real parts, then the system is, we call stable, just stable. Okay? That's the eigenvalue. Or you can look at this way. If you don't want to solve eigenvalue, if you are too lazy to solve eigenvalue, and then you look at your mass matrix, your K matrix and zeta matrix, and to check if they are positive, definite or positive. So that's one way to look at the system stability. And another way to look at system stability is look at the energy decay. Look at the energy decay. Or check the matrices M, zeta, and K. Look at energy decay means you check the matrices M, zeta, and K. But anyway, eigenvalue also the you can look at energy decay. All right. So in control, to see the system is stable or not, again, you can look at eigenvalue of the system or look at the positive definiteness of the M and zeta to K. Two ways to do it. For the ABA, for this ABA, then we look at the just the mass matrix and stiffness measuring and zeta and W matrix. All right. So far, we discussed only the direct feedback. Now I'm going to talk about dynamic feedback. What do we mean dynamic feedback? Right. And you know that if you do have the control course, I think you might learn already dynamic feedback. So here we are going to discuss the dynamic feedback. What do we mean dynamic feedback? Okay, let's look at the chart. Okay, I think it's easier to look at a chart. Okay. Now, again, we have a system, very simple system, M and K, and this is the simplest you can get. All right, but there's a dynamics you have to compute from your computer. Not just only the gain. If you look at earlier, the slides earlier, then you will be able to see, I think it's done again. The computer is now, if you look at earlier, what we did was just the U really, we are, I think we are coming too quick here. So our feedback force will be UC is our feedback force. For example, now this UC is not just simply gain multiplied by the output you have. Right? If you check earlier slides, maybe a few slides earlier, you can see that my gain is simple, just the, right, let me go back, it's easier. If we look at the earlier slides, okay, like this, or like that, all right? If you look at these earlier slides, then you will be able to see now my control force is nothing but U equal to minus zeta W. Right? There's no other state, only one single degree of freedom. That's it. Now, what I'm going to talk about today is a different concept. All right? A different concept here. You have to worry up. We have to look at this different concept. All right? Okay. Different concept here. All right. Now let's see. There's a state. There's a degree of freedom called WC. See, did you see the WC here? And the compute. Then we'll have called UC here, This WC and this W is a real state, real displacement. WC is not real displacement. WC is my computer displacement. It has nothing to do with the real system's displacement. This is the imaginary state, the displacement. So we have the real displacement. We have called imaginary displacement. That we just imagine we have another degree of freedom called WC. So here we have W, that's the physical displacement. And where WC, which is I call imaginary. Displacement.